Computing Minkowski sums is a fundamental geometric operation needed in many applications. We have recently developed a software system for the construction and usage of Minkowski sums of convex polyhedra in three-dimensional space, which we'll call polytopes for short. The Minkowski sum of two sets, for instance the orange cube and the blue tetrahedron, is the union of pairwise sums of all the points in the sets, one orange and one blue. The greenish-yellow polyhedron is the Minkowski sum of the cube and the tetrahedron. As the cube and the tetrahedron rotate, their Minkowski sum changes. If the operands rotate, the entire structure of the sum changes. If the operands translate, the sum only translates. The main features of our system are completeness, exactness, and efficiency. We have collected about 500 models of convex polyhedra and have conducted extensive experiments which demonstrate these features. The key structure that we use is what we call cubical Gaussian maps. A cubical Gaussian map of a polytope is the central projection of the famous spherical Gaussian map, or normal diagram of the polytope onto the unit cube, an axis parallel cube centered at the origin, whose edges are of length 2. The projection forms 6 planar maps, each associated with a unit cube face. The cubical Gaussian map on the right is the dual representation of the tetrahedron on the left. For example, the dual of the blue facet of the tetrahedron is the blue vertex on the unit cube boundary, and the dual of the green edge and the red vertex of the tetrahedron are the green edges and red faces on the unit cube boundary, respectively. The primal representation can be reconstructed uniquely, as each face of the planar maps is extended with the coordinates of the corresponding primal vertex. The reason we use this flat representation is that it is strongly supported by the arrangement package of the Computational Geometry algorithm library. Once the operands of the Minkowski sums are represented using the cubical Gaussian map, the Minkowski sum operation amounts to computing the overlay of these maps. It is well known that two polytopes collide if, and only if, the Minkowski sum of one polytope and the reflection of the other through the origin contains the origin. The lower left quadrant shows the workspace. It consists of an orange cube and a blue tetrahedron. The lower right quadrant shows an auxiliary space, where the cube is reflected through the origin. The upper left quadrant shows the configuration space. It consists of the Minkowski sum of the tetrahedron and the reflected cube. The upper right quadrant shows the unfolded cubical Gaussian map of the Minkowski sum. Note how the origin in the upper left quadrant penetrates the Minkowski sum as the tetrahedron and the cube collide, and escapes the Minkowski sum as the two polytopes separate. A distinctive feature of our system is its seamless handling of degeneracies, as in the case where the two operands are identical icosahedra. The two maps are identical, and their successful overlay means merging overlapping segments and vertices of the underlying planar map. Another feature of our system is the output sensitivity of the algorithm. Here you see the constantly updated sum of two rotating geodesic spheres. Here you can see the cubical Gaussian maps of some of the polytopes in our collection. We also compared our method with the naive approach of computing the convex hull of the pairwise sums of vertices of the operands. On the geodesic example, our software is more than 50 times faster than the convex hull approach. Our software is available for download and use.